Hey there, Algebra 2 students. Welcome back to Ms. McGuire's classroom. Today we're going to be doing Unit 7, Lesson 3. Our main topic is exponential growth and decay. Exponential growth and decay. Don't forget to put your first and last name, period, and the date in the upper right-hand corner of your paper. Our objective today is I will identify the key features of exponential models and their functions, describing whether the model represents exponential growth or decay, and mastery will be demonstrated by scoring at least 80% on the extra practice. So the first piece of this that we're going to discuss is exponential growth. So exponential growth will always use an equation in the form of y is equal to a times b to the x. And so how this is kind of different than models that we've used so far is that the variable is in the exponent. So you're taking this constant number b, like b doesn't change in the equation, to the x power. So what do each of these things represent? Well, in exponential growth, a is your initial amount. So A is your initial amount. So when we are talking about like exponential growth, we're taking this initial amount and we're going to see it grow over time. Then we also need to identify B. B is our growth factor. So B is our growth factor. A was our initial amount. B is our growth factor. And when you have exponential growth, B has to be greater than 1. To have exponential growth, B has to be greater than 1. Then to find B, B will always be equal to 1 plus R. And R represents your growth rate. So R will always represent your growth rate. So another way that you could rewrite y equals a times b to the x, you might also see exponential growth equations like this. Y is equal to a times 1 plus r to the x. So we can replace b with 1 plus r, since b is equal to 1 plus r. So sometimes you might see it like that as well. And then every time you have exponential growth, an exponential growth graph will always rise to the right and fall to the left. So the end behavior of an exponential growth graph will always be down and up. So we're decreasing to the left and we're always increasing to the right. So exponential growth increases over time. All right. Now, when we talk about exponential decay, I'm actually going to take that off of my notes because we're not going to talk about end behavior with these graphs. Okay, so when we talk about exponential decay equations look the same as growth. You still use y is equal to a times b to the x. A is still your initial amount. So exponential growth and decay have a couple of things in common and a couple things not so in common. So A is still your initial amount. But this time, B is your decay factor. And remember, if B was greater than 1, you have exponential growth. If B is equal to 1, you're not going to have any growth. So for exponential decay, you're decay factor is going to be less than 1, but greater than 0. So it still has to be positive, but it has to be less than 1. So for example, B could be 1/2, 0.7, 0.89, 0.77777. Okay. And then to find your decay factor, to find B, you take 1 minus your decay rate. So R represents your decay rate. So again, this B could be replaced with 1 minus R. So Y is equal to 1 minus R to the X. Okay. I think that's everything we need to know about our exponential decay. And oh wait, we haven't talked about the graph. Here we go. I knew I was forgetting something. Okay, so kind of how exponential growth rose to the right, exponential decay falls to the right. So exponential decay will always fall to the right and rise to the left. All right. So now we're going to decide, for example 1, whether or not each of these equations represents an exponential growth or an exponential decay function. So the way we're going to look at this is, for example 1, part A, g of t is equal to 3.5 to the t. So as you can see, our variable is an exponent, so we have an exponential growth or decay model here. What we need to look at is our b value. So for this function, g of t is equal to a times b to the t. A would have to be 1, and b is 3.5, and then your variable obviously is t. So 1 times 3.5 to the t is 3.5 to the t. So that's how I know that there's technically a 1 times the 3.5 out in front of here. That means that my initial amount is 1. And since b is 3.5, 3.5 is greater than 1. That means I have a growth factor, and that growth factor is 3.5. So then how do I find my growth rate? Well, remember, b is equal to 1 plus your growth rate. So if b is 3.5, and that has to be equal to 1 plus r, subtract 1 to both sides, r is equal to 2.5. So my growth rate is 2.5. All right, now actually I'll do part B with you. So for part B, again, our exponential models are always in the form of y is equal to a times b to the x. So we can see that a, our initial amount, is 250. B is 0.065, and 0.065 is less than 1 and greater than 0. So this time we have a decay factor. And our decay factor is 0.065. To find our decay rate, remember b is equal to 1 minus r. So 0.065 for my decay rate is equal to 1 minus r. I'm going to solve for r. I'm going to subtract 1 to both sides. And we're going to have, if I can get this open, 1 minus, just kidding, sorry, 0.065 minus 1, negative 0.935 equals negative r. So if I divide both sides by a negative, I get r is equal to 0.935. So my decay rate is 0.935. And if you think of 0.935 as like a percentage, our decay rate then would be 93.5%. And for over here, 2.5 then would be 250%. So remember, when you change a decimal to a percentage, you just move the decimal place to the right twice. All right. So why don't you go ahead and do part C and part D on your own. So identify, are these exponential growth or decay models? Identify the initial amounts, identify the growth or decay factors, and identify the growth or decay rates. Go ahead and give it a shot on your own. So as you can see with part C and part D, for part C, I decided that this was a growth, exponential growth function because B is greater than 1. That makes my initial amount 3. My growth factor is 5. And my growth rate then would be 4 because 4 plus 1 is 5. Then for part D, our B value of 0.5 is less than 1 but greater than 0. So that means we have exponential decay. My initial amount is 3, my decay factor is 0.5, and my decay rate is 0.5. Or you could think of that as 50%. And then our growth rate over here would have been 400%. Or we're quadrupling is another way of thinking of 400%. All right. So now we're going to look at these 4 graphs in example 2 and decide if these graphs represent exponential growth or exponential decay. So if you look at the graph in example 2, part A, does this represent exponential growth or decay, or neither? So hopefully you chose neither, because this is a parabola, right? This graph represents the function y equals x squared. So that is not exponential growth or decay. The variable is not an exponent. What about part B? Is this exponential growth or decay, or neither? So hopefully you decided it was exponential growth. And we know that because it looks like our exponential growth model that we have on the first page of our notes, where we are increasing to the far right and decreasing to the far left. All right, what about part C? Is this exponential growth, decay, or neither? And this would be exponential decay because we have a decrease over time to the right. And then part D, is this exponential growth, decay, or neither? And this is neither. It does not follow the pattern of behavior that we said all exponential growth or decay models will have. In fact, this should be the graph of y is equal to x cubed. Again, our variable is not an exponent, so this is not an exponential function. All right. So now let's practice graphing some exponential models. So y is equal to 2 times 3 to the x. So right away, the first things I'm going to identify are the initial amount, the growth and decay factor, or the growth and decay rate. So y is equal to 2 times 3 to the x. Our initial amount would be this 2. Remember, we're basing this off of y is equal to a times b to the x. So our initial amount is 2. Our growth factor is 3. And we know that it's a growth factor because that b value of 3 is greater than 1. Our growth rate then is 3 is equal to 1 plus r, so r must be 2. All right, so let's get this thing graphed. So to graph these, I'm going to plug in some negative values, 0, and some positive values. We're going to see what our function does. So let's start with this. We're going to have y is equal to 2 times 3 to the negative 3, 2 times 3 to the negative 2, 2 times 3 to the negative 1, 2 times 3 to the 0, 2 times 3 to the first, 2 times 3 squared, and 2 times 3 cubed. So let's start with 0 first. 3 to the 0 is 1 times 2 is 2. 3 to the first is 3 times 2 is 6. 3 squared is 9 times 2 is 18. 3 to the third is 27 times 2 would be 54. 2 times 3 to the negative 1. So 3 to the negative 1 is 1 over 3. So 2 times 1/3 would be 2/3, or 0.66 repeating. So 2 times 3 to the negative 2 would be 2 times 1 over 3 squared, or 2/9, which is even smaller than 2/3. 2 times 3 to the negative 3 would be 2 times 1 over 3 cubed, or 2 times 1 is 2 over 3 cubed is 27, which is even smaller than 2/9. So I'll show you what's happening here on the graph in just a second. So the first thing is we need to decide how we want to number our x and our y axes. I'm just going to count by ones on the x-axis. Don't forget to put your dashes and number every other one. For my y-axis, I'm going to count by, let's just count by 2. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Let's see, -2. And again, we'll just count by negative. Okay. There we go. So let's plot the first point. So the first point, I'm actually going to start with my y-intercept of 0, 2. And notice that y-intercept of 0, 2 matches our initial amount. That's where this graph technically starts, at 0, 2. All right. Then we're going to plot the point 1, 6. So 1, 6. And then 2, 18. And then off to the negative side, we see that these numbers, as x gets smaller, as x goes from -1 to -3, these y values here of 2/3, 2/9, and 2/7, our y values keep getting smaller and smaller and smaller. So like 2 divided by 9 is 0.22. 2 divided by 27 is 0.074. So these numbers keep getting smaller. It looks like we're approaching 0. We're getting closer and closer to 0, but we aren't actually touching 0. Like we never reach it. So what's happening is these y values, so at -1, it's less than 1. -2 is less than 1. We're getting closer and closer to that x-axis, but we're not actually touching it. So when you draw on your graph, you're going to show that your function is getting closer and closer to that x-axis, but you don't want to cross it and you don't want to go below it. It is not possible. Oh, no. Accidentally erase. There we go. For our initial amount of 2 to get smaller than 0. Like you can't get a negative amount. Like if you started with 2 grams of flour, 2 grams of flour, and as you go to that, you're not going to go to that negative side, obviously, with time, but it might get closer and closer and closer to 0, but it's never going to go below 0. And that example was a terrible example because you could start with 2 grams of flour and then end up increasing it over time, I guess, if you go and buy more flour. Anyway, never mind. Ignore me. Okay. What I'm trying to say is you're not going to end up with a negative amount of flour. So we're not going to cross that x-axis and go to those negative y values, is what I was trying to say. All right. So for part B, y is equal to 2 times 0.3 to the x, why don't you go ahead and identify the initial amount, growth and decay factor, the growth and decay rate. So that equation was y is equal to 2 times 0.3 to the x. And go ahead and identify those things really quick. All right, so our initial amount is 2. We have a decay factor of 0.3. Our decay rate, so 0.3 is equal to 1 minus r, negative 0.7. So r is 0.7. Our decay rate is 0.7. Right. So now I want you to work on graphing this on your own. So again, you can go ahead and just use the same x values we used before. You know, use some negatives and then go down, use 0 and then go up to like positive 3. So what I noticed is that as my x values increased, my y values actually got smaller and smaller and smaller. And so what's happening is over time, our graph starts to approach the x-axis off to the right, but doesn't actually touch it. It doesn't cross it and go below it. It just gets closer and closer to it. And then to the left, we're rising. So when I plugged in like -3, I got a big number of 74. When I plugged in -2, I got 22. If I were to plug in -4, I'd get a number even bigger than 74. So we're increasing off in that left direction. All right, now let's do some word problems. So you really can't do exponential growth or decay without doing some word problems, but they're kind of fun, so don't worry. They're interesting, okay? So I know I just said word problems are fun, I'm sorry. Suppose you deposit $1,000 in a college fund that pays 7.2 interest annually. Write an equation to represent your money's growth over time in T years. How much money will be in the account in 5 years? So we're talking about investing money in a college fund that's paying 7.2% interest annually. So this is an exponential growth model, because I'm sure you don't want to put your money into an account and watch it like go away, right? If you're investing it, you want your money to grow on that investment. So we're going to use our exponential growth model where b is equal to 1 plus r. So when I write my equation, I'm going to say y is equal to a times b to the x, but for b, I'm going to use 1 plus r. So that 7.2 interest, we are plugging in a percentage. We need to change it to a decimal. So 7.2% would be the same thing as 0.072. You got to move that decimal place twice to the right. Okay. So when we plug this into our equation, it's going to look like y is equal to, our initial amount is 1,000 times 1 plus r, then 1 plus 0.072 to the x. So our equation is y is equal to 1,000 times 1.072 to the x. And that's the equation we're going to use to answer the next question. So how much money will be in the account after 5 years? So what we're going to do is, oh, I just realized we were supposed to use t for our variable for time. There we go. So, and then I guess to be a little fancier, we also should have said f of t instead of y for how much money will be in that account over time. Our y value is a function of time. So how much money will be in the account in 5 years? We're going to find f of 5 is equal to 1,000 times 1.072 to the 5th power. So f of 5 is equal to, so you're going to take your calculator, if I can get it open. There we go. We're going to take, what I recommend you do is take 1.072 to the 5th power first, and then multiply that by 1,000. And you're gonna get 1,415.7. So it's 0.8, so I'm gonna round to 1. And I have $1,415.71 as our final answer. So in 5 years, we'll have $1,415.71. So all we did was we took $1,000, put it into this savings account, and it's gonna make us $400 in 5 years without us doing anything. So imagine if you had added more money each year and that initial amount got bigger and bigger, your money would grow even more over time. So we love exponential growth when it comes to things like money. It helps make our money work for us instead of us working for our money. All right, let's do part B. So part B, a radioactive element decays at a rate of 5% annually. There are 40 grams of the substance present. So write an equation to model that scenario. So this time we are decaying. So we're going to use exponential decay. And our function for that is y is equal to a times b to the x, where for your decay factor, you use 1 minus r. You subtract your rate from 1. Okay. And we're still talking about years annually, so we're still going to use t for time. So let's do this. So let's write our function. So the function of that time would be equal to the initial amount of 40 times 1 minus 5% is 0.05 to the t. And so if I go ahead and subtract that, I'm going to have f of t is equal to 40 times 0.95 to the t, right? Okay. So how much of the substance will remain in 30 years? So you're going to take 30 and plug that into our function for t and see what you get. Go ahead and give that a shot. So when I plugged 30 in for t, I got 8.6 grams. Notice it said to round to the nearest 10th. So you should have rounded that 5 up to a 6. And then I added the word grams because we always want to include our units in these problems. When will the amount of the substance drop to below 20 grams? So we can see that within 30 years, we're down to 8.6 grams. So in order to find how many years it'll take to drop below 20, we're just going to try out some different numbers. So I know when I plug in 30, I get 8.6. So let's see what happens when we plug in 20. So we're just going to take our function. We're going to take 0.95 to the 20th, and we're going to multiply that by 40. And we get 14. Okay. So I still have less than 20 at this point. I'm trying to find when we hit 20. So let's do even less years. Let's do 10 years. So let's do 0.95 to the 10th times 40, and we get 23. So we're getting closer. Let's try 5. 0.95 to the 5th times 40, and we've got 30 grams. So 5 gets us 30. So that means it needs to be between 10 and 5. Maybe some of you have already found it. Let's try 8. What happens when I do 8? So 0.95 to the 8th times 40 is 26.5. Oh, you know what? I just realized I'm on the wrong track, huh? Oh my gosh, that's so silly of me. My bad. I'm trying to drop below 20. So when at 10, I hit 23. At 20, I had 14. So I should have tried plugging in like 15. Oh my gosh, let's pretend like we didn't waste our time with those. Let's try 15. I bet some of you are yelling at the screen right now, huh? To the 15th times 40 is equal to 18. Aha. So it's between 10 and 15. So let's try 12. So 0.95 to the 12th. Later in this unit, you're going to learn how to solve for a variable when it's in an exponent, and you won't have to do all this guessing and checking. Ooh, there's 21. So it's between 15 and 12. Let's try 13. 0.95 to the 13th times 40 is 20.5. And let's try 14. 0.95 to the 14th. I'm so silly sometimes. Times 40 is 19.5. Okay, there it is. So somewhere between the 13th and 14th year, we drop below 20 grams. So let's just say after the 14th year, the amount of the substance my calculator, let me move it. Drops below 40 grams. All right. Cool. Or you could have said sometime between the 14th and 13th year, our substance drops below 40 grams. Either of those would work. All right. So now what I want you to do is I want you to learn how to move this calculator. There we go. All right, I want you to actually do part C on your own. You're given a population of a town, and you're just gonna answer some questions about that population. So, oh, I should give you a hint though. So when you do, you're given the initial population in 1890, and they wanna know the population in 1915 and 1940. Take 1915 minus 1890 for the amount that you're gonna plug in for your time t to figure out the population in those years. Okay, so like for 1915, you would plug in 25. For 1940, you would plug in 50, and so on. Okay, so go ahead and give that a shot and see what you get. We'll compare answers in just a second. All right, so I'm just going over the answers. I'm not showing my work, so I'm gonna know whether or not you just copied what I did or if you actually tried yourself, because you should have some work on your paper. So to write an equation that models this scenario, the function would be f of t is equal to 6,250 times 1.0375 to the t. When you plug in f of 25, you get around 15,689 people. You're not going to write a decimal when you're representing people, so make sure you either round up or round down to the nearest whole number. F of 50, in 50 years, there'll be about 39,000 people, and that would be in 1940. The population in 2023 would be 836,177 people. And then I noticed that by plugging in 133 to get to the year 2023, I got around 800,000 people. So that's pretty close to 1 million. So I just plugged in numbers that were close to 133, but higher than that. And then to figure out where that crossover from the 900,000s to 1 million would be. And I found that it would be between the years 2027 and 2028 is when the population of small town will reach 1 million people according to this model. So go ahead and go get your extra practice done. Let me know when you're done so we can go over it together, and I'll see you back in class. Have a good day.